Where we left off, I just wanted to quickly return to problem of the day number 1. Omar had asked a good clarifying question, and I realized after we moved on that I had, sorry, let me just back up, had not told you quite the correct information here when we went through this. So Omar had asked about the overall charge of this complex, and what I had said was I had this mixed up. So the complex, the starting material as drawn was correct. So let's, the starting material should be charge neutral, and we'll go through electron counting in much more detail later in the class. So if this is at all confusing to you, don't worry. But this stems from the fact that this ligand is -1, this ligand is -2, aluminum is +1. So this fragment has an overall -1 character that's charge balanced by the +1 potassium. So overall, this is charge neutral. And then when the cation is abstracted through the complexation to the crown ether, now you no longer have this charge balance. So the overall complex is -1, and there's a cation outer sphere. And then that holds, that same logic holds as you go through this sequence. So these should all be overall -1 complexes. In this case, now you have -1 from nitrogen, -1 from this nitrogen, and then -1 from each of these 2 ligands. So this too is an overall -1 complex. So thanks for catching that, Omar. I did want to make sure to clarify that since I had gone through that quickly. And I'll just provide that reference in case anybody missed it from the chat window. This is from Jose Gocochea's and Simon Aldrich's collaborative paper back from 2019. So feel free to check that out for more details. One of the cool things, just as I'm jotting this out, is that this process takes place under very mild conditions and is at or near room temperature, and is actually fully reversible. It's a fully reversible CC bond cleavage of benzene / bond formation to reform benzene. So this, again, the point of this example was not only to foreshadow some reactivity that we'll see down the road, but also to just highlight how much cool new reactivity or unappreciated reactivity is left from the fundamental studies of main group chemistry. So just to run through some of the things that we covered towards the end when the connectivity started breaking up, we were talking about different reactions to form organometallic reagents. And the category we were talking about was exchange reactions. So these include reactions where we take the metal in its metallic state and react it with a preformed organometallic to perform a form of transmetallation. Another reaction that can be categorized as transmetallation is organometallic type 1 plus organometallic type 2, reacting those, and then having the reaction effectively exchange the 2 metal partners. A third type is type C here. This is an organometallic reagent plus a metal halide. And so some of you may have seen this type of transformation where you take an organolithium and then you react it with a magnesium halide salt as a means of forming a Grignard reagent, for example. And then the driving force here is that the metal that is ultimately forming the new interaction with the halide in this overall halide metathesis sequence should be more electropositive, such that it forms a stronger ionic interaction. We then talked about metal-halogen exchange reactions, which are powerful ways of generating typically aryl organometallic species. And so this chemistry also is probably familiar. I imagine many people in the class have done this sort of transformation where you can take, for instance, sec-butyllithium or tert-butyllithium plus an haloarine, and typically the halide should be bromide or iodide. Chlorides typically don't work, and fluorides rarely work in this chemistry. You can just assume they never would work due to competitive benzyne formation. And again, an important consideration is the overall thermodynamics of this process, and thinking about having R groups that are more favorable for stabilizing negative charge as a thermodynamic driving force. One of the things I realized that I didn't go over, but I anticipate there might be some questions about, so I just wanted to draw your attention to the mechanism by which these metal-halogen exchange reactions can take place. And there are two possible pathways highlighted here. And so the first one is one in which the organometallic, the organolithium reagent, and the organohalide react through open shell intermediates, through radical intermediates that are held together within the solvent cage. So I've tried to denote the solvent cage here in cartoon form as with this yellow highlighter. And then they can recombine, now having swapped their partners to deliver the products. And another way that these can react is through what's called an 8 complex. You'll hear this nomenclature throughout the class. It's also an important concept in transmetallation in the context of cross-coupling reactions. And 8 complex just typically refers to a net negatively charged organo main group element adduct that is thus primed for group transfer. And so in this case, an 8 complex can form between sorry, this should be so a sigma bond is formed between the halide, the halogen atom, and the incoming nucleophilic carbogenic substituent to make an overall negatively charged 8 complex adduct. And then essentially this process can happen in reverse, but the other way around, such that the outgoing R group is lost. And I'll just note here that it has been shown that 8 complexes of this general type can also decompose to generate radical species. So the boundaries between these two processes, they're drawn as if they're totally distinct, but actually is in many cases not clear. Problem of the day number 2 was one that Noor helped us with. And this was a discussion about the nature of why N-butyllithium in THF solution is unstable. Noor had rightly talked about the effect of ethereal solvents of breaking up organolithium adducts that will be something we discuss here shortly. But after they're broken up in this way, now basic butyllithium can deprotonate the alpha position of THF. That can be represented in this middle structure here, the alpha lithiated THF. And then of course, in terms of the underlying reactivity, it can be thought as the alpha anion, and this can rearrange to generate ethylene, which of course is a gas and provides strong thermodynamic driving force because loss of ethylene will be irreversible. And then the lithium enolate form of acetaldehyde. So this connects to another means of generating organometallic species from one organometallic species from another, which is where an organic fragment is reacting as a CH acid. That's effectively what we see here in this THF case, although in this case that the resulting intermediate is unstable. But we take an organometallic species, we react it with an acidic proton, and then we can get the corresponding metallated R prime metal species with loss of the now protonated form of the original organometallic. And then there are some special processes that take place with Organomercury species, and one that actually connects to a topic we'll cover in more detail in the CH activation lecture is mercuric acid's ability to break less acidic CH bonds. So for example, aryl CH bonds through loss of HX, formation of the intermediate mono organomercury species, and then further reaction to give the diorganomercury species. So this mode of reactivity where you take a metal X2 species, lose HX to make a metallated intermediate is something that will look familiar in the context of like a CMD type pathway with palladium chemistry. So a lot of that it finds its early roots in the stoichiometric organomercury chemistry. So let me just add a couple bullet points from my note sheet here before moving on. So this organometallic plus CH acid approach requires alkali metal species, and then is controlled by the kinetic CH acidity. The site selectivity is controlled by the kinetic CH acidity. Again, I think we had been able to cover this before the connection lost, so I'll go through this quickly, just in case people were coming in and out. There are various ways to form organometallic species from a category of mechanisms called insertion processes. This includes metal hydride plus alkene or alkyne. This should be very familiar from hydroboration chemistry. This process can also be catalyzed by transition metals, and we'll see this later in the class. For example, catalytic hydrosylation is a very industrially important process. And some of you probably have also done hydrozirconation reactions, which is an interesting subtype in its own right. Additionally, by the same logic, rather than transferring a hydride in the metal to the pi system, you can transfer a carbogenic group and the metal to a pi system in a process called carbometallation. And here I just note that typically in organometallic species that possess both a hydride and an alkyl fragment, here I'm thinking alkyl aluminum organoaluminum species like dibol, diisobutyl aluminum hydride. These will typically transfer the hydride in preference to the alkyl substituent, and that's largely governed by sterics, hydride being of course small and alkyl substituent being much larger. And then another organometallic to organometallic transformation here that is relevant, and we'll come back to this in a later class too when we talk about transition metal catalysis, are reactions in which carbene can react with organometallic species to now generate a new organometallic species. In this case, it's an SiH insertion process driven by loss of nitrogen gas. Okay, and then the fourth category of reactions to generate organometallic species are elimination processes. These are a little bit less commonly encountered in your day-to-day synthetic pursuits. The first type are decarboxylation processes. Here, this is illustrated with some reactivity in the organomercury field. So for example, mercury dichloride can undergo initial anion metathesis with a sodium carboxylate salt to generate a mercury dicarboxylate salt, which then under thermal conditions can extrude CO2 and generate a mono or di organometallic, the di-organomercury species. And traditionally, this process has been found to work best with organic fragments that have some electron withdrawing group, for example, aryl substituents or fluorinated alkyl substituents. And another way to generate organomercury species is arylation of diazoniums. Here too, we're foreshadowing some reactivity that we'll come back to later in the context of the Matsuda-Heck reaction. In this case, with mercury dichloride, treatment with an aryl diazonium salt can lead to aryl transfer to the mercury center. I have this drawn as silver, but this should be an aryl group. Let me correct that. So an initial formation of this adduct here, where mercury is interacting with one of the chloride substituent from the diazonium. Extrusion of nitrogen then drives formation of the aryl mercury species that can be, sorry, I have this misdrawn too. You can tell I was rushing here, and also eyeing the connectivity issues at the same time, and so getting sloppy with my chem draw. So this can form the monoaryl mercury species or the diaryl mercury species. Again, I would say this is a less common process. You'll very likely never run this at any point in your career as a chemist, but it's still important to understand and appreciate this early reactivity. In case this is unclear, this says the R group contains an electron withdrawing group. Okay, so let's talk now about what I think is one of the more fascinating aspects of main group organometallics, which are their unusual, or at least unusual to people who don't think about it every day, structures. And I think this ultimately stems from the fact that many of the constituent atoms involved, lithium, magnesium, and aluminum, are quite small in nature. So they can form aggregate structures, bridging structures, et cetera. And here, part of, I think, what makes this fascinating is it overturns a lot of what we learned when we first encounter these reagents in introductory organic chemistry. We draw them as nicely monomeric, well-defined species, and then in solution, of course, their properties are far more complex. So having an understanding and appreciation for that, understanding when you put reagent X in solution, what is actually formed, and then how you can perturb that for your desired application, I think is important, and hopefully one thing you can take away from this section. So let's first talk about organolithium species. These are typically oligomeric, both in solution and the solid state. There's been some really beautiful mechanistic work over the years on this. Heroic studies, including things like getting single crystal X-ray diffraction on solid form tert-butyl lithium. That gives you an idea of the type of ingenuity that has been brought to bear on this field of study. So these are typically oligomeric. So let's first take the case study of N-butyl lithium. And the aggregation state of N-butyl lithium is dependent on solvent medium, and that's, I think, a common theme throughout this section. So if we consider the structure in diethyl ether, it is tetrameric. So the way that there are different ways that can be represented. I've shown one representation here where each lithium atom is represented in black as the vertex of tetrahedron, and then each face is a N-butyl group. And here's an equivalent representation of that structure, just using a different coding system where each lithium is drawn in black, and you can see the embedded tetrahedral here if you connect the dots between the black atoms. And now each N-butyl group is drawn in red. And as you change to a less polar solvent medium, namely cyclohexane, you can drive the structure to being hexameric. And so a way to think about how this hexameric structure is formed is basically on an additional lithium atom approaches one of the faces of the tetrahedron and increases the nuclearity of this sort of core structure. In these cases, all these cases, the N-butyl groups or the overall structures possess these 4-center 2-electron bonds. And so I've tried to kind of depict that in cartoon form here, where you have 2 electrons that are formally belonging to this N-butyl group, but really are distributed across the carbon of the N-butyl, as well as the 3 lithium centers. And what is perhaps unsurprising, but also adds to the complexity, is that these aggregate units, individual aggregate units, can also interact with each other in solution, and particularly in the solid state. So this gives these species some of the properties listed, for example, low volatility and also low solubility, because they have this propensity to form aggregates and then can crash out. So let me reopen my screen. So let's consider another case here, the case of phenolithium. And phenolithium in ether as solvent can be drawn similarly to what we saw in the case of N-butyl lithium. And I've drawn out like a chemical formula representation here to highlight some nomenclature or some terminology that will become useful throughout the class. So here, the phenyl group is denoted as mu3, and mu denotes a bridging interaction, and then the superscript denotes the number of atoms that are bridged by this particular ligand. So in this case, it's a mu3 phenyl substituent, and you'll see that again. And one of the things you may have encountered in your synthetic organic pursuits is that these aggregates can be broken up. And so that's depicted here by reaction of phenolithium aggregate with TMEDA, which leads to formation of a bimetallic species where each of the TMEDA caps one of the lithium atoms, and the phenyl groups here are now switched to mu2, bridging two lithium centers. And we'll soon talk about the structure of organoaluminum species, and this TMEDA adduct of phenolithium is isostructural to phenyl triphenylaluminum. I had talked about the ability of these complexes to aggregate and in some cases precipitate, and that's exactly what is seen in this case of CP lithium. CP here stands for cyclopentadienyl. This is a common ligand in coordination chemistry. It's formed from deprotonation of cyclopentadiene, among other ways. And so CP lithium can form this polydecker sandwich complex. So this is like an infinite Big Mac sandwich, bun, patty, ad infinitum. That's what CP lithium is in its solid state, and that's been confirmed through various early studies. Okay, let's move forward to organomagnesium complexes. And so here a key concept that I want to emphasize is the Schlenk equilibrium. So let me highlight this. Where rather than what we typically draw on the page, which is our magnesium X, where X is typically bromide or chloride, what is actually formed in solution, or I should say, this species exists in solution as a mixture between the diorganomagnesium and magnesium dihalide salts. And I'll let you think about how exchange happens, but to give you a hint, this is very much analogous to these alkyl bridging or aryl bridging interactions that we saw above in the case of the organolithiums, and we'll see below in the case of the alkyl aluminum species, organoaluminum species. And so, though we draw this without any defined three-dimensional structure, in solution, Grignard reagents exist as these tetrahedral, in tetrahedral geometry. L here is solvent, where they're bridged by the halide substituents. So here we would call these mu2 halides. And one of the important points is that the diorganomagnesium adducts that are formed through the Schlenk equilibrium are in fact much more reactive than the mu to halide bridged forms that are also present in solution. So let's zero in then on what the actual structure of one of these di-organomagnesium adducts would look like. Here, keeping in mind that magnesium prefers to be tetrahedral. I'll draw this in tetrahedral form just so I can be crystal clear with what we mean here. And so on. So if you ever see me do this, it just means and so on, or that's sort of the repeat unit. So it forms these polymeric 3-center 2-electron bridges. And while this is polymeric or oligomeric in nature, it is nevertheless extremely reactive. There are some exceptions. These aren't always, strictly speaking, always polymeric, where when the R group is bulky, and this would make sense if you just think about this intuitively. If you start bulking this up from a primary carbon to a secondary, tertiary R, then the ability of this to bridge decreases dramatically. So this can be monomeric if R is bulky. And so we often handle or Grignard reagents in ethereal solvents. So let's consider that case now formally in terms of what the actual solution state structure looks like. So this is a tetrahedral solvate. So if we draw the chemical formula as such, and how that looks is as shown here. So let's consider the case of THF, just as one example. And then if you think deeply about this, it also allows you to even predict some reactivity patterns. So let's say, for example, you have a THF adduct or you're handling a Grignard solution in THF and the reactivity is not as high as you need for a given application, then you could instead consider using an alternative solvent like 2-methyl THF, which is going to give you a more nucleophilic form of the Grignard by virtue of having a less stable magnesium oxygen interaction through steric clashing. And I've used this trick once myself to great success and was very impressed with myself. Okay, let's consider now problems of the day 3 and 4. So I think everybody should be following along this recording. So now take the opportunity to pause the recording, pull up problems of the day 3 and 4. I'll pull those up briefly so you can refresh your memory on what those are. And then give yourself 2 minutes to think about each of those problems. Write out a couple sentences, either type them out in your email or write them out freehand and then take a photo of it and then email your rapid response to Van as a record of you having done this and given it some thought. And that will be a way of us tracking that you're following what's going on. So pause the recording now, give that a try, send your response to Van and she'll keep an eye out for it. And then resume the play, and then we'll discuss the answer when you're ready. I'll pull up the sheet now and read out the problem so that we're all on the same page. So problems of the day 3 and 4, they both have to do with the reactivity of Grignard reagents, hence why we're covering them in this part of the talk. So I'll read out problem of the day number 3, reagents of the type, and then it's R, magnesium chloride, lithium chloride adduct are called turbo-Grignard reagents due to their increased reactivity in reactions such as metal-halogen exchange with aryl bromides. And some of you will recognize pioneering contributions by Paul Noschell's group in this area. So propose a structural rationale for the observation that this turbo-Grignard reagent is more reactive than the parent Grignard reagent. And then problem of the day number 4 is a two-parter. But both related to the same idea. So the first is that part A is the addition of 1,4-dioxane to Grignard reagents is known to dramatically increase the rate of Grignard addition reactions, for example, to carbonyls. Explain this phenomenon, thinking back to what we just covered in terms of the Schlenk equilibrium, and then based on the answer to part A, try to predict the products of the reaction shown before, where we take this di-Grignard and then react it with dioxane. And of course, all of these processes where you react a Grignard in solution with something are equilibrium processes and thus have a thermodynamic driving force. So that's why this is denoted as equilibrium arrows. And then there are two products here. Okay, so take a minute to think about that, and then we'll discuss. Okay, so first problem of the day, number 3, about turbo-Grignard reagents. I think the first thing to do is to draw out what we think the adduct that is formed upon addition of lithium chloride would actually be. And I think that helps us understand what's going on here. So let's consider our generic Grignard structure in coordinating solvent. So we have 2 L-type ligands. We have our halide substituent and then our organosubstituent, and then we're adding to it lithium chloride. Now, magnesium, as we've seen, likes to form bridging adducts and also likes to be tetrahedral. Lithium, the same way, prefers to be tetrahedral. So what can be formed here is a bimetallic adduct. Sorry, I'm just going to change the position where I'm drawing solvent. L here are just the coordinating solvents as we discussed. So both of the, I'll simplify this further by just drawing this as a chloride. And I think that's what's drawn in the problem anyway. So both of the chlorides can engage in these mu2 bridging interactions where they bridge 1 magnesium center and 1 lithium center. And so at first glance, then you might be wondering, well, this actually looks like it's maybe a more stable adduct. So how could this be more reactive? But here we get back to what we covered at the beginning of class about electronegativity. So remember that lithium, as compared to magnesium, is a more electropositive atom. And so in these bridging structures where lithium was replaced with magnesium, you would imagine magnesium wanting to pull more charge density and having a stronger dipole here that ultimately decreases the electron density in this. So it's all about the anionic charge density here, right? So by having a more electropositive atom here, you're able to accumulate more negative charge density on the anionic and thus nucleophilic carbon center. So that is the origin of the enhanced reactivity that is observed in these so-called turbo Grignard reagents. And I'll just very quickly provide a reference here that was one of the handouts in case you're interested in reading more about this. Just bear with me while I pull up this reference. Okay, so this was problem of the day number 3. How about problem of the day number 4? So here it's asking about the empirical observation that addition of dioxane enhances reactivity of Grignard reagents. And so let's think back to our Schlenk equilibrium. I'll scroll back here so you all remember this. And it's essentially asking, how is this Schlenk equilibrium perturbed upon addition of dioxane? So let's copy this so we have it handy down below. Number 4. I'm not sure why I can't paste. Let's try this again. So how does this equilibrium change upon addition of dioxane? And it turns out that dioxane can form insoluble aggregates with magnesium dihalide salts. And so you can challenge yourself to draw this, how this might look in 3 dimensions. But the key point is these are insoluble and they crash out of solution. Thus, by Le Chatelier's principle, as we pull this out of solution, now we force the equilibrium further in this direction. As we saw above, the diorganomagnesiums are highly reactive. And so this too, I think, has some practical ramifications. If you're running a Grignard reaction and it's not performing as well as you might hope, try adding some dioxane to drive the Schlenk equilibrium to the more reactive form of the Grignard. So this is part A. Part B now asks you to apply this to one particular Grignard reagent, and the structure of that is shown here. So now, just applying that same logic, remembering that we're going to precipitate out a magnesium dihalide dioxane adduct. So let's just draw that as our product B. That's a good place to start. And then how about adduct A? Now, if we just balance the stoichiometry, we see there's a 3-carbon bridge with 1 magnesium left. And now you have 2 open coordination sites that, let's just say, they're going to be occupied by solvent. So this makes a magnesium-cyclobutane structure. Okay, now let's cover our last class of organometallic reagents and wrap things up. The last class that we'll cover are organoaluminum reagents. Some of the same themes that we saw above here too apply. We'll cover a couple different case studies. So the first case study is aluminum or trimethylaluminum is, I think, how you typically think of the reagent, but in reality, this is a dimeric reagent. So the molecular formula is aluminum 2 methyl 6. And here you have these interesting mu2 methyl groups that bridge 2 different aluminum centers. The aluminum, like we saw above with magnesium and lithium, prefers to be of a tetrahedral structure. You see, in reality, it's just in the case of trimethylaluminum, it's a distorted tetrahedron. I've highlighted here the bond angles. You see distortion around the tetrahedral carbon, and as well as distortion around the aluminum center. And these are examples of 3-center 2-electron bonds. I've drawn a quasi-MO diagram here to show you what the bonding picture looks like with sp3 hybridization of both carbon and aluminum. And one of the interesting empirical observations here is that the reactivity of organoaluminum species in general is highly attenuated in ethereal solvents. And it's been postulated that the comparatively slow development of organoaluminum chemistry and organic synthesis had to do with the fact that a lot of the comparative studies where folks would look at organolithiums, organomagnesiums, and organoaluminums in parallel would be performed in ethereal solvents, where it's known now and well appreciated that organoaluminum compounds are much less reactive. And so in terms of just the overall bonding picture of this 3-center 2-electron bond, you can think of this as being isostructural to a carbenium, an intermediate or transition state, depending on your perspective, of a carbenium ion rearrangement, like a 1,2 alkyl shift. So that's the same structure, and concepts that we'll cover in class are isostructural and isolobal, meaning the same arrangement of atoms and the same molecular orbital depiction, respectively. And so that this is a way to think, if it helps you to think by analogy, that this is how to think about what those structures look like. Now, in the case of triphenyl aluminum or aluminum 2 phenyl 6, we have a mu2 phenyl group, so that very much analogous to what we saw above in the case of the methyl the methyl substituents. Similar molecular geometry. The one that I just want to highlight is how we see this distortion from a perfect trigonal planar geometry that we would expect in a phenyl group to now starting to see some tetrahedral character, so deviation from the 120-degree bonding angle, suggesting sp3 character on that carbon center. Okay, so the last thing that we'll highlight before closing out is some reactivity. And I would just draw your attention, in the interest of time, we won't go through example after example after example. Here I would direct your attention to the reactivity handout that accompanied the lecture. You should have gotten that from Van. So please, please take a look at that for more examples. And again, I think it's interesting to think about the reactivity consequences of basic principles. So let's think back to one of the first things we covered in class, which is the electronegativity of the atoms that are involved in these structures. So we saw that lithium and magnesium are relatively electropositive as compared to aluminum. And so that allows you to predict how covalent or how ionic the corresponding carbon metal bond would be. And so indeed, in the case of organolithium and organomagnesium reagents, as we've seen, I'm sure you've encountered at this point in your chemical education, these are highly reactive with polar functional groups, such as carbonyls, nitriles, or conjugated alkenes, so-called Michael acceptors. And again, this has to do with the fact that the carbogenic substituent in these atoms has high carbanion character, and thus can interact with these functional groups, which have relatively low-lying pi star LUMOs. And then in contrast, organoaluminum reagents, by virtue of having a less polarized carbon metal bond, are now capable of adding to unpolarized CC pi bonds as found in alkenes and alkynes. And this process is known as carboelimination. Some of you might have run such reactions. The reaction proceeds, at least initially, in a syn stereospecific manner. There are some interesting examples where syn stereospecific addition of an organoaluminum to an alkyne is followed by cis-trans isomerization, but that's outside of the scope of what we'll cover today. And so let's just draw out kind of a mechanistic depiction, and then a mechanistic depiction of what's going on here, and then also the consequences of the mechanism and how we can understand that through the rate law. So let's consider triethyl aluminum. As we've seen over and over again, this is dimeric in solution. And so for this to react, the first thing that has to happen is equilibration to the monomeric form. So fast equilibrium followed by the rate determining step, which is the carboelimination process. Here I'm going to draw this as a stepwise process that proceeds through the corresponding carbocation. And then out pops your product, where you've had ethyl transfer to one of the alkenyl carbon atoms and aluminum transfer to the other. So because of this, this sequence of events that has to happen before the rate determining step, where you get dissociation of the dimer, and the rate law for this is we have half order in the organoaluminum reagent, and then first order in the alkene. Let me draw the alkene here. The relative reactivities here, I would bet if I asked you to just predict this based on first principles, you would be able to predict this. So here I'm just drawing the relative rates as a function of the alkene substitution. And so the most reactive is ethylene, followed by monosubstituted alkene, followed by 1,1 disubstituted and 1,2. And so this difference between 1,1 and 1,2, I think, helps corroborate the notion that you get substantial positive charge buildup in the rate limiting step. And I probably would have gone through this more quickly and left out some details in the actual live class since we're running low on time, but I'll just take the opportunity to provide just a little more interesting kind of case study of the reactivity of organoaluminum reactions. So as you can see, one of the reaction partners that does work well here is ethylene. And so you can imagine if you think about what the product is from reaction with ethylene, you get another organoaluminum species, and you could imagine this happening ad infinitum. And proceeding on and on and on. And so I've drawn this multiple arrows here that's happening at all three reaction sites repeatedly. And so this is called the Aufbau process. Developed by Carl Ziegler, a Nobel Prize winner at the Max Planck Institute, where I worked for 1 year as a Fulbright fellow. I used to walk by Carl Ziegler's Nobel Prize every day on the way to lunch. And then these now growing alkyl chains on the aluminum can be reacted sequentially with O2 and alcohol. And this leads to long chain primary alcohols. And these ultimately are used in the production of surfactants. I think that's an interesting early application of organoaluminum with obviously huge impact in the industrial sector. So I'll wrap things up here. Again, I apologize for the connectivity issues. I hope this follow-up lecture was covered everything that you may have missed due to the connectivity problems. Please contact me, Van, or Tanner at any point with questions, and otherwise I'll see you on Thursday. Thanks for joining.